cloud. Oops. Sorry. All right, let's get started. So today's workshop, we're going to be covering basically how neural networks work. Or actually, we're going to assume you have some bit of knowledge, but we really don't need to know too much about it to get started. So let me start presentation mode. So this is kind of intro to AI, but part 2. If you weren't here last week, I recommend you watching or 2 weeks ago, recommend you watching the video. So for review, here's a quick review. What's a neural network? A neural network is basically a model that tries to approximate some function. So think of like x squared, or like some more complicated function like cosine of x squared or cosine of sine of x times e to the x or something. Like it approximates really random functions. It's composed of neurons that work together to transform input data into desired output data. You can think of neurons as like same thing as brain neurons, and the way they work is basically they take a bunch of inputs, weight it together, do some transformation of that data and produce some output. A typical deep learning method is to stack layers of neurons on top of each other, enabling fast learning and prediction. So you see on the right picture is basically a really simple 5-layer network with 3 hidden layers. The first layer is always the input layer. The last layer is always the output layer. And the layers in the middle are known as the hidden layers, where it's basically the memory of the model. It's learning and trying to approximate functions. In particular, the model on the right is good enough to approximate a function that can recognize digits from an image. And we'll show you how to do that real quick. So how do you train a network? If you recall from last time, a network is defined in behavior by its weights, e.g. theta 0, theta 1. In a neural network, we have things called weights and biases, which you might have heard of before. These define the connection between the neurons. So each of these lines has a weight associated with it. These basically define the network and define the overall behavior. So if you look at a graph on the right, this is an example of a graph between 2 parameters and the loss function. The loss function is basically evaluating how well our network is doing. So one example of a loss function would be mean squared error. If you don't know what that equation is, it's basically taking the true value, subtracting what we predicted, summing and squaring that, and then summing all of that and taking the mean. That's mean squared error. There's many other loss functions. There's things called binary cross entropy loss, which is very popular. The sparse cross entropy. There's a lot of loss functions. And basically what we want to do is you want to find the part in this graph here that is correlated to the least loss. And so you see this point here. Oops, it's really hard to see actually. This point here is where the least loss is. So you want to find that point. What you will also notice is that when we train a neural network, this loss landscape, this curves, isn't very easy to follow. The way we train neural network is we take stepwise movements towards what we think is the global minimum. Someone just asked a question, loss function shown as gradient descent, right? So what you're seeing on the right is called gradient descent, the steps we're taking to go to some minimum. But a loss function and gradient descent are 2 different concepts. A loss function kind of defines how we evaluate the network and will affect the gradient calculation. We use gradients, hopefully you guys know some calculus, but we use gradients to find a direction that takes us towards the least loss. So you see in these different points, these little lines represent the direction to least loss. And what you'll also notice is that if you start at different initial starting points, you'll end up going to different places. So let's say we follow this contour, we follow it down the slope like a ball, we'll end up here. But if we started up here or started up here, we follow it down, we'll end up here. So you can already think about that. Just a lot of problems with gradient descent is that sometimes if you start in a bad position, you'll end up in a not so good position. You'll end up in what's called a local minimum instead of like a global minimum. If any questions, feel free to spam me in the chat. But yeah, any questions about how neural networks work in general? And just remember, I recommend you guys check the video out from last 2 weeks ago, or maybe search up an online tutorial on just a quick, brief intro into what neural networks are. I highly recommend the YouTube channel 3 Blue Round Brown. They're very good at this. But yeah, anyway, let's get started coding. So what today we're gonna use Keras, which is an API built into the which is an API developed by Google, which makes deep learning exceedingly easy to do. Basically, and what we're gonna do today is we're gonna try to recognize digits. So Keras offers an inbuilt library, which can be found here. It allows you to create your own dataset class and make a load data function to load your data, create your own class. etc. It just makes it easy to load your own data and do things. So let's go quickly look at our data and see what it looks like. So I'm gonna run this. So it's currently downloading the data. Don't worry about the setup code. The setup code is very specific. You can just copy online. But the more important thing is learning how to visualize. So let's import Matplotlib. If you don't know what Matplotlib is, it's basically a visualization library or plotting library specifically. And one of the things you can do is it can plot images. So what we just loaded is Xtrain. Xtrain is actually 60,000 images of size 2828, and they're all grayscale. So let's take a look at one of them. So here we have a number. I have no idea what this is actually. This could be like a 5. It can be like a really weirdly written like 4. I don't know. But you can start looking at these images. You can take a random index, look at another image. This looks like 6. And the way this data is structured is that there's also a Y train. And if you look at this, I'm going to add a title to this. This will say this is labeled as 6, which is correct. This is the label. So remember in machine learning, usually in in the realm of supervised machine learning, which is what we're taking you through today, is we have a model and we want to improve it by using labeled data and input data or training data. So Xtrain, Y-train is our training data. Xtrain is like the inputs, which are images. Y-train is the outputs, desired labels, which is the labels like 6, 1, 2, 3, all the way to 9 and 0. Any questions so far about this? Okay. Whenever you're making neural networks, I highly recommend learning how to plot or visualize what you're doing. Matplotlib.pyplot is a very, very popular tool for plotting these things. And I won't be going to depth on what these functions do, but you can take a look at these things later. it basically just shows images, and title just adds a title. Cool. So now you might be wondering, why do you have another set of data, X test and Y test? What is this for? So if you recall, the way machine learning works is that we want to be able to evaluate our network. While we are training on the training data, theoretically, we will always do better every step. Like every single step, we improve, we run gradient descent, our model will always perform better. So what we want to do is, how do we evaluate now? Well, you could evaluate on the training data, like basically how much of the training data you predict correctly. Oops, I don't want to do this. But there's a big issue with that. If you're trying to evaluate your network on the training data, it doesn't say much. One of the issues with neural networks is that they have a high capacity to overfit. Overfitting means basically you're doing super well on the training data, but you do really poorly outside of the training data. So what you'll notice is that a neural network can easily just memorize the training data and do really poorly. At which point is that's really bad. You don't want to do that. So that's why we have test data or validation data. Test data allows us to empirically evaluate our model as it trains. So the moment that test data stops improving, like the accuracy on test data stops going down or going up, we might want to stop training, because at that point, we've reached to the point where our model can't seem to learn any better. All right, any questions so far? Okay, I'll be right back. Something just knocked at my door. All right, so now we're gonna look into splitting data. So let's look at this. So yeah, so to address our issue with just training and evaluation, we're gonna split our data like so. So what we did here, what did we do? What we did is basically, we took our training data and split into a ratio of 70% to 30%. Why do we do this? Again, remember, we want to be able to evaluate our network while it's training. So let's go to the next section. Defining your neural network model. So in Keras, it makes it really easy to define how your model works. For example, this network here looks really messy and complicated, but this actually takes like 4 lines of code to write. So here we're showing an example. what we're going to do here is we're going to use what's called the Sequential API from Keras. Sequential API lets us define basically really simple stacked linear deep networks like this. So let's show an example, and I'll go step by step of what each step does. Let's create our network. By the way, if you don't know where this code is, I'm going to paste it into the chat. GitHub should automatically render it, and you can kind of follow along. So let's look at this function really carefully. So let's make a model, create network. Network input. How does he do it? So what's happening here? Activation is not defined. Oops. Oh, sorry, give me a second. Sure, this is not defined. Oh, oops. That coding is very hard. This should be it. No, requires one. Oh, okay. Give me a second. I'm trying to figure out what's happening here. Just can you find it here? Okay. Sorry, the code has a little bit of a mistake, as always. Very difficult. All right, here's the model. So let's look at the summary. So something that Keras provides is providing summaries. Nope, that is not the summary. We have to build it first. My bad. Something is wrong here. Okay, let's assume by calling build or fit. Specify input shape. Oh, sorry, there's something wrong here. Nope, that's not it. Input shape equals. Sorry, I'm not quite sure what's happening here. I thought this code was working, but it's just not. There we go. Okay. A couple bugs, unfortunately, but we move. So what's happening here? Oh, sorry. Actually, something is wrong here. My bad. That's not right. It should be network 0 shape. Okay, so what's happening here? When we're creating a network, we first initialize the sequential API to create a model. Then the first thing we do is because we're working with image data, it's a 2D matrix of 28 by 28, right? So recall that when we plotted it, this is basically a 2D matrix of pixel values or grayscale intensity values. So like here in the dark areas, it's about 0. The brighter areas is like closer to 1. 1 being bright, 0 being unbright. So what we do is to pass our network through something linear like this, we need to decompose our 2D image into a 1D representation. So the way we do that is super simple. We use flatten. The flatten layer is basically the layer in between the raw input on the left and then the input layer. So what we're going to do is we're going to flatten our data and it'll convert the shape, the dimensions of our matrix, right? From 2D to 1D, in particular, it converts a 28 by 28 pixel image into a 784 values, basically. And then once we have our 784, our really long, high dimensional vector that represents our digit in image form, we then pass it through our network. So the first thing we do is we have a dense layer. A dense layer is also known as a fully connected layer. Also known as a linear layer because it's linear. Our dense layer is basically these hidden layers here, these neurons. So for using Keras, when we do dense 25 and then specify activation ReLU, a couple of things are happening here. One, we're telling the network to first send the output of the flattened layer directly into this dense layer. then this number here, and yes, Devang is correct. This number here, the first number he passes as an argument to dense is the number of neurons. So for example, in this image here of 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 neurons. That would be equivalent to adding a dense layer like this with 9. But we're not going to do that because 9 is too small. We want to use more. And then the other thing we can specify is activation. So activation equals ReLU. This means that we give it what's called the rectified linear unit activation function. So let's take a look at our activation functions. There are many activation functions. We have a funny little graphic here kind of demonstrating the different kinds you can have. So we have sigmoid, which is very typical and common, tanh, step function, stop plus, ReLU, soft sign, ELU. I don't even know some of these actually. I think some of these are not right. Like swish is actually the same thing as sigmoid. But yeah, there's many different activation functions. But what are activation functions? If you remember last time, activation functions basically defines or tells the model how do we transfer the input into some kind of output. So if you don't remember, ReLU is very simple. Is basically this guy here. ReLU is very, very commonly used in computer vision, which is what we're doing here. And basically what it does is that if the input is less than 0, the sum of the weighted input is less than 0, you output 0. If the input is greater than 0, you output the input. Simple as that. So that's this layer here. And it basically converts our 784 high dimensional vector representing image into a lower dimensional representation that's composed of 25 dimensions, of just 25 values. 25, sorry, 1 dimension, but 25 degrees of freedom. That's a better word. Oh, for those who are joining late, there will be a YouTube video of this later, so you can watch the beginning. So don't worry about it. So anyway, let's move to the next step. Do you guys understand how this kind of converts a 784 length vector into a 25 length vector? From 784 degrees of freedom to 25. All right, if you ever have any questions, feel free to stop me. So now we're going to move to the final layer. So this is important. What are degrees of freedom? So this is how I describe the number of variables. It's a very common term to use in computer vision. So like, for example, when you have like 725 variables kind of that can change, that represents your degrees of freedom. Like every single variable can move in some direction, and that's like a movement of freedom, right? So think about in the real world in 3D, you can move in 3D, 3 directions, right? Technically, you can move along the x-axis, z-axis, y-axis. Like think Minecraft, if you guys ever played it, you can move along 3 axes, right? So that's technically 3 degrees of freedom. There's actually a lot more math involved. There's actually 6 degrees of freedom that represent any transformation in 3D space because there's something called rotation space, which is known as SL3, but you guys don't need to worry about that. That's very complicated. But yeah, that's just how I kind of say there's this many variables that can change. Anyway, once we get our 25 length vector, we now want to use this downsampled information, this kind of learned abstract information, and try to predict labels. What do we want to predict? Well, what's our task? Our task is take an image, predict the label. So for example, if you're seeing here, the label is 6. If you take another one, label is 1, and we have a 1, for example. So that's our ideal goal. So what we want to do is we want to have output neurons for every single possible label. And what do these output neurons represent? The output of each neuron is going to represent the probability that it is of the same label class. So let's recall a bit of computer science. If you have 10 output neurons, right? So let's say there's 10. Each output neuron is going to represent a single label. So a really easy way to represent it is the 0th neuron, the first one, or 0 index neuron, is going to represent the digit 0. First neuron represents 1, second neuron represents 2, sorry, 1. Third neuron represents 2, so forth, until we have 9 digits. And yeah, Devang is correct. The last layer is 10 neurons because there are 10 possible digits to predict. So that's why you want to have 10 probabilities. And so and then our final prediction is basically whichever probability is the max, the highest, we take that label, and that's our associated label. Now you might have not heard of this activation. There's an activation called softmax. This is very common, but this is an activation function used in multitask classification. So what is softmax in general? I don't think it's in here. Yeah, it doesn't really kind of fall under there. But what softmax does is basically it normalizes our data. such that every single output, the sum of all the outputs of this layer equals 1, which makes sense, right? If you think back to probability of anything happening can only, the probability of all events happening, right? The sum of all of them should equal 1 at all times. So in our probability space, right, we have the probability of outputting is 0, 1, 2, all the way to 9. There are 10 different probabilities. We want to make sure that since it can only be one of those, the sum of all of them equals 1. So that's what softmax does. It just kind of normalizes it and converts very low dimensional representations of this 25-line vector into readable, understandable confidence scores. Anyway, let's create our network. We know our model, what our model does. What's the next step? And now we got to train our network. So let's go get our network and let's get the training code. So it's very easy. We can train without validation and we can just kind of look at this. Oh, sorry, I forgot to talk about loss. So we in Keras, we use the model.compile function, and what it does is compiles a model with a loss function. Our loss function here is called sparse categorical cross entropy. You do not need to know what this means. It's a bit beyond the scope of today, but basically it's a very typical loss function used when you're dealing with multi-classification. When you have multiple labels, when you have more than 2 labels, you want to use this cross entropy loss. There's many reasons for using this, but one of the main reasons is that this function is very easily learnable. So remember we had that loss landscape. If you choose something like mean squared error loss, like how far away your label is from the actual label, it does really poorly. Mostly because the loss landscape is very weird. It's not very easy to follow and go down to a local minimum. But when you do a sparse categorical cross entropy, that loss landscape is actually really easy to learn. It's much more convex. Anyway, we say optimizer equals atom. This is a special optimization function or method. The method that we show here is called gradient descent, which would be, I think, labeled as SGD. Atom is actually much more advanced and it's much faster, and we use it here because it's just much faster. So we're going to use that. But basically, atom kind of stems from the thought of SGD, of using gradients, but it adds a lot of other important features that allows your network to not encounter local minimums. Anyway, so we're going to now fit our model, and we're going to see, oh, what the? Kernel appears to have died. It will restart automatically. I'm sorry, I don't know what just happened here. Let me try this again. Oh. Terribly sorry about that. I don't know what's wrong with my Python. Is this like TensorFlow's new version is not working or something? Oh, that's not good. Sorry, I don't. Maybe TensorFlow's new version just got changed or something. Just a bug in the code now. Okay, I'm sorry. I don't know why that's not working, but I'll show you what's supposed to happen. What's supposed to happen is when you call fit, it will show you the training over time. It will show you like a little progress bar. It will show you how long each step took. Each step being basically taking one batch of data, which in our case is batch size 8, iterating over it and updating your model accordingly. And so you can see this loss function kind of decreases over time. Another thing you want to notice is that we also try another way, which where we use validation data. So we can pass in using validation data equals x val, y val. So you see that during training, the training loss, the first loss function metric here, is always going to go down. But you will notice that the validation loss doesn't really go down at the same speed because one is different data. And the reason why it doesn't go down at the same speed is because the validation data is not being trained on by our model. The model is trained on the training data. So we want our model to be able to be generalizable such that it can learn the correct features by doing its best on the training data while also doing well in the validation without ever have seen the validation. And you kind of think of like this, right? If you've never seen a set of data before, but you still do surprisingly well, that kind of just means that whatever experience you have, it's pretty good. Yeah, so epochs is like the number of trial and error tests. So the way supervised machine learning works is basically trial and error. You kind of just run a trial, you look at the error and then you backpropagate it, you tell your model, improve from this error, learn from your mistakes. But specifically an epoch is more understood as basically one iteration through all the training data. So you see that our epoch basically goes through 5,250 steps. Each step, it goes through 8 data points. Our in total, if you do some math, it has 42,000 data points. That's actually the size of our training data. So that's why this has 5,250 steps. And once it finishes all the steps, one epoch finishes and we output metrics. Yeah. Any questions about this? Okay. I don't know why this is here. Let me try this in Colab. Maybe Colab is a different version of TensorFlow that might work. And I don't think everyone has a Jupyter notebook. It's free, but not everyone's necessarily gonna have it. So let me open a random notebook. New notebook. I'll explain it in a second. So give me a second. Let's call this. We don't need to show that. Outdated steps. Our network. We can display a short summary of what it looks like. So that's our shapes. And then let's try fitting it again. Okay, there it works. Okay, I think my local version is kind of broken. So you see how this loss just kind of like decreases over time, which is really cool to watch. And you'll see how it's finishing over time. And let me just kind of reiterate what these different things do. So when you call the fit function on your model, so after you create your model using Curious, you want to call the fit function. And what does fit do? Fit in machine learning always basically just means make your model do well on the data. Fit it on the data, basically, right? So if you guys in your physics classes or like math classes, you probably learn a line of best fit. That's basically this. You're trying to find the quote unquote line of best fit. But in our case, with a neural network, it's a very, very high dimensional hyperplane. You're trying to find this really good hyperplane fit. And not even plane, it's actually just a high dimensional curve. So what we're doing here, so we're doing x equals x train, y equals y train. What does this mean? It means our x input data, our independent variables, is going to equal x train, and our labels, the things we want to predict, is going to be y train. So it's going to learn to do really well on that data. And we're going to set epochs of 5. So that means we're going to do 5 runs over all the data, iteratively improving our model. And what does batch size mean? So batch size basically means how much of the data to learn from each step. So we will see that we have 5,250 steps. Each step runs over 8 data points. So why do we use batch size? Batch size is really helpful in improving your learning speed. So we can compare speeds real quick. So let me create a model, new model. And I'm just compare speeds. You'll notice that when you set a batch size of 1, it's much slower. Do you see how the ETA is like 47 seconds? It's much, much slower. And there's a lot of reasons for that. Basically, when we're working with neural networks, the way neural network learns is that it does a bunch of matrix operations. When you're dealing with matrices, you typically want to deal with bigger matrices because it lets you do a lot more parallel computation. There's a lot of math behind that. You don't need to really worry about it. In particular, when you do a batch size of 1, our matrix is small, right? Our input data is 1 sample times 28 times 28 images. But when we put a batch size of k, or 8 in our case, it will be an input size of 8 times 28 times 28. And once you flatten it, it'll be 8 times 784. And you see how we have a bigger matrix? With a bigger matrix, we're kind of doing more computations in parallel. So you can kind of think of like a batch size of 8 will kind of do 8 computations in parallel. So you notice, I mean, it's not exact at math, but you notice that 7 seconds times 8 equals 56 seconds. That's about how long this thing takes. Yeah, so there's a lot of talk about how do you choose the optimal batch size. It's a very, very, very difficult thing to do. But in general, what we will notice is higher batch size equals much faster speed, but it doesn't always correlate with less accuracy. So there's a couple issues. I can show you guys a picture later, but basically when you do a batch size of 1, you're doing what's called online learning. Basically, every time you have a data point, you're going to learn on it. You're going to completely fit on it. But this enters a lot of issues. When you have online learning, you tend to have very erratic training behavior. So let's look at stochastic. descent. Let's see, where's that image? Here we go. Here's a really good image. Basically, the green line here is mini batch descent. This is what we're doing. Batch gradient descent is also kind of what we're doing. This is stochastic. Stochastic is very messy. This is why the loss is not actually going down. So you just notice that when we do a batch size of 1, you see how the loss function only reaches 1.5, whereas when we did a batch size, it went down to 0.9. You can understand it through this graph. If you're doing every single iteration and update it, sometimes you're going to update for the better for all your inputs, but sometimes you're going to update for the worst. Like it will happen to work for this for training point K, but for training point K plus 1, it actually does worse. Does that make sense, everyone? Okay, yeah. But when you batch things together, you kind of normalize your data and you kind of learn more stuff together, which is more generalizable than learning one thing at a time. Because when you learn one thing at a time, sometimes you might learn the wrong thing and then you start going the wrong direction. So yeah, that's basically what that means. So yeah, I'm gonna stop training because this is actually not doing very well. And you notice if you do like batch like 32, this go like super fast. Yeah, 1 second. And you notice the loss actually goes down pretty fast as well. But I think what you also want to kind of see is how well does this do on our training validation data, right? So let's look at how our model is doing. So we can actually just pass in data here. Let's pass in the X files. So validation predictions. This would be all our validation predictions, and it'll have the correct shape. These are labels. Yep. And you'll notice that X file has a shape 18,000. So we have 18,000 data points, 18,000 images, and let's plot some of them. So let's look at one of the images, and let's see how we did. So the first image we have is, nope, not prediction, sorry, X file. The first image we have is a 1, right? Let's see how our model did. Our prediction, we predicted 0. Oops, sorry, I need to do one more step. So our predictions, you'll notice it's a shape of 18,000 by 10. This means there's 10 variables in each one. What we need to do is we need to do something called argmax. What is argmax? It basically means you want to choose a index or argument that relates to the highest value. So let's look at this. We see our first image prediction. We predicted 9 different values. We predicted basically 0, a 1, basically 0, 0, 0, 0, 0, 0. And this makes sense, right? In the first index, that represents us predicting the value 1, which is correct. We actually did predict it right. And you can use this function here really nicely to tell us label. So we're gonna do that. So let's change this a bit. Let's do np.argmax, all that. So now our shape should be like just 18,000 values. Oh, sorry. I need to comment. So axis 1 here just means to pick the highest value for each sample, not among all samples. So now we should have 18,000 predictions. Now we can see our predictions. So cool, we predicted a 1. Let's take a look at another random one. Predicted 7, that seems correct. And so forth. So you can see how powerful this machine learning is, right? All of a sudden, in about 10 seconds, our model is able to predict digits just from a 28 by 28 image. Any questions so far about this? Okay. And this is just some nice syntax. So once you have your model, if you just pass in data into it like this, like you call it like a function of data, it'll give you the outputs of the output layer. So feed it in data into this first layer, it'll give you these output data. Cool. So now let's look at our validation accuracy. How good is our network actually doing? So let's look at the accuracy here. I'm gonna do model.fit. So we're gonna create a new model and we're gonna fit it. So while we're gonna let it run in the background, let's get our code ready to then make our predictions. So we're gonna pass in this X file to see our predictions, and we'll see our validation loss now. What you'll notice, interestingly, is somehow our validation loss is much lower than the training loss. Now, why is that the case? I actually don't know. This is actually just random chance. Usually, what you should expect is that validation loss will hover around training loss, but you always want it to be lower than training loss, hopefully. If it's a little bit above training loss, that's fine. But if it's really above training loss, that means something is wrong. And you notice that the moment that training loss goes below our validation loss, what does this mean? Do you guys have any ideas? What does it mean when we go under the validation loss? And especially when our validation loss starts going back up. What does this mean for our model? Correct. So we're basically overfitting now. If our validation loss is going up, that can only mean one thing. It means that we're not learning the generalizable features to do well. And even though we overfit a bit, we actually still do okay. Like, I mean, if you just look at a couple examples, it looks fine. It still predicts a 9. But maybe perhaps for maybe some harder examples, I don't know what are harder examples. Oh, here's an example of something erroneous, right? We predicted a 2. This is obviously not correct, right? This should be a 3. So how we want to address this? Different things. We want to try maybe like, let's not train until here. That's not a good idea. Let's maybe just train for 40 talks and see how our model does. And let's do like 32 batch size to make our thing maybe normalize data better. So this should train really quickly, and let's see how it does now. Cool. So we're seeing validation loss go quite low, and this should be the lowest it ever reached. Oh, nice. So our validation loss is 0.5/6. Did we do this better? Nope, we still predicted it too. Okay, this is just machine learning. Machine learning is very random. It won't always get everything right, but you'll notice that it actually did do better. Yeah. Any questions about this? Okay, so this is a bit of NumPy and math. So let's kind of just look at what argmax does. So if you don't know what argmax does, let's take a look at a graph. Is there a good graph of this? Here we go. So let's say we have some function here. Let's say we have some parabola like this, and you know what? Let's just get decimals. This will looks ugly. There we go. We're gonna look at 2 graphs. So what are we doing here? So what is the maximum of this parabola? The maximum here is 4, right? But what is the argmax of this data? The argmax is 0. And what does this mean? Argmax is equal to the input value that achieves the maximum value, right? So let's look at our validation predictions again. When we do model xval, remember this produces a matrix of 10 values for every single data point, right? And these 10 values represent our confidence in how likely it is that particular digit. So let's do this again. Val predictions. And we'll notice that val predictions is of shape 18,000 by 10. Yeah, we want to select the index that corresponds to the maximum probability. So let's take a look at this first example, right? We have a lot of different probabilities here. We have this really small value, this very small value that's equal to a very small value. No, actually, sorry, this is the largest value. This is 0.999. Something close to 0, something close to 0. So when we're looking at this output from our matrix, right, we have 10 values. We want to choose the index, right, that corresponds with this 9.9, 0.99, which is the highest probability. Because we know that the index of the highest probability is equal to the correct label, right? It's our predicted label. So what does argmax do? So when we apply argmax, it will take an array of a matrix, and it'll give you the argument or the index corresponding to the highest probability. And we'll see this instantly, right? This is the highest probability, 0.9995. That's definitely our highest. So Devon asked a question about what axis equals 1 means. So this is a bit of matrix manipulation, but you'll notice that when we have val predictions, it's of shape 18,000 by 10. So what does the axis mean? The first part of our shape, which defines our rows in our matrix, is axis 0. The second part of our shape is axis 1. So when we do np.argmax, the default value of axis is actually 0. It says none, but that means 0. So what this would do is, oh, that doesn't make sense. Okay, default value is axis 0. I don't know why it did the other thing. So when it does that, it'll tell you the index of the value of the highest probability. So you notice that here, that's not quite right. Oh, I see what's wrong. So I think in this 12 array, you will have the highest probabilities in here. Like something like this is like higher than the ones before. But when we specify an axis, if we specify an axis 1, this will take the argmax per every single data point. So basically for every single data point among the 10 values in the first axis, choose the index that has the highest value. So if we do this, you notice that we have an array that's 18,000 elements. Every single one of them represents the index in each data point that corresponds to the highest probability. Any questions about this? Okay, cool. Oh, so there's 18,000 data points. If you recall, when we made our validation data split, right? Xval has 18,000 data points. Yep. And specifically, when you call shape on an array that's defined by TensorFlow or like NumPy, it tells you basically the dimensions of each of your matrix and how many elements are in each dimension. Okay. Yeah, that's basically it for the coding workshop. All the code is hosted online. I feel like right now the current version of Keras has a bug or something. I don't know why. So you might want to try running this yourself on Google Colab, which is free. If you have a Google account, you can just go to colab.research.google.com and you get instant access to a Jupyter notebook. Anyway, let's go to the final thing. So we also, this might be hard, but I highly recommend you to try it out, is we have a neural network competition. So if you head over to our website, ACM AI at UCSD, we have basically a competitions running. One of our competitions is the neural network competition. And you can see that people uploaded things. So how does this work? This is kind of like what we just did today, but what we're going to do is we're going to give you test data and we're going to give you training data. So what your objective is, you're going to use a training data, which is a list of points in 2D space, and you want to predict the third value. So basically, we have a 3D function hidden on the back end that you want to try to approximate. So I can show like an example. For example, here, this is basically representing the XYZ values. So you're going to take the first 2 values, you want to predict the third value. How does this work? Basically, this is starter code for you to do it, and this looks really similar. So ignore everything here. This is just code to kind of load the data. What you want to write code for is this part here. So you notice this whole API is the same thing. Remember, we're adding a dense layer of 10 inputs. We're putting activation linear. We specified an input shape 2 because we have 2 dimensions. And we want to use atom optimization. You want to use mean squared error loss or something. So we have to do all this stuff. You want to create the best model that will best predict a neural network. Sorry, best predict the function. And you can see how these people are ranked right now. This leaderboard is actually what's called the public leaderboard, which represents your mean squared error loss on the test data set, which is all the data in this file here. And this test data set doesn't have the Z value. You see how it's blank? You need to fill this in to submit. So basically create an account, you can click, so let's say I log in, go to competitions, clicking there, upload predictions, you're gonna upload your test CSV file. Once you upload it, you'll get your ranking, you'll see your score history. So you can see how people's submissions are varied over time. I think our winner was this guy. He's a high school student at some other random high school. We got a pretty good score. I don't know how, but he did some insane tricks. Anyway, how to compete, starter codes here, highly recommend to look at, and just submit your CSV file to this here. If you have any questions, just ask us in the Discord. We'll be there to help you. Yeah, and here's our code if you want to use it. That's basically it for today's workshop. If you have any questions, feel free to ask them now. Otherwise, I'm going to stop recording and I'll share the replay, the recording with Ishan, so you can share with all you guys later. How do I stop the replay? Oh, pause it, stop recording.